So what will happen is, to make the synchronization between two processes, the Peterson solution is the software solution. To actually fulfill the requirement of the software solution, we have also some hardware solution which will implement the critical section code, and it will give the solution to the critical section problem. So many systems provide hardware support for implementing the critical section code or critical section problem. Here, generally, we'll use a concept called lock. So in the hardware, we use the concept called lock. Locking is the concept. What is locking? Locking is nothing but, we have the idea of locking in the hardware solution. Here we try to protect the critical region via locks. So just like your, let's say in the hostel, you might share the room with other people or other friends. So this lock will be actually your pass to go to the shared resource. So your shared resource is, let's say you assume that you have a room, and at a time only one person will be in the room. So how you will fulfill this particular alternation? You will fulfill this alternation with the help of the lock, and lock has only one key. And if one is going in, then other people cannot go in. And if one is going out, then other people can go in. Means your room you assume as a critical section. This critical section is nothing but shared resource. If one process want to execute the shared resource, it has to take the lock. And once it will go out, it has to give the lock to other people. So it happened in that way. So here in the hardware synchronization, we'll use the concept of lock. Okay. Now, one more thing we have to see here is, whatever hardware solution that we are going to see in this particular lecture is for the uniprocessor, where we have only one processor exist in the system. So we talked about what do you mean by uniprocessor, what do you mean by multiprocessor, what do you mean by hyper-threading, and those concepts we have already been seeing. Now uniprocess means only one processor is there to execute the instruction. It means that only one instruction will execute at one time. So you assume in that way. And there are uniprocessor system and could disable interrupt. So there is no interrupt. There is no interrupt means there is no preemption at all. Currently running code will execute without preemption, generally too inefficient in multiprocessor system. So this type of assumption is not at all suitable for the multiprocessor system which we are using today, but it is one solution, hardware solution, but there is a limitation of only one process, as well as we doesn't have any interrupt, as well as we doesn't have any preemption. Operating system using this not broadly scalable. So this particular solution is not scalable. So in today's computer, we do not use these type of solution. In previous days or the old days system, we use this type of solution. Modern machine provide a special atomic hardware instruction which is called atomic non in the modern system. So either we can use this assumption, or if we are using modern system, then we have to make sure that whatever instruction that we are talking about, it is atomic. Atomic means, so hardware has some instruction, okay? So there is some instruction which will be executed by the CPU. That hardware instruction will be executing in one CPU cycle, right? So let's say if we have one cycle, So you see, in one CPU cycle, we are going to execute the instruction. So it is just like 0 or 1. This is just an instruction. Either will execute 0 or the 1. So bit, you know that bit is the lowest unit of storage, and to reference to that, the atomic is. So 0 cannot be further divided, or 1 cannot be further divided. But if we have the instruction like 0, 0, if we have the instruction like 1, 0, if we have the instruction like 1, 1, these can be divided, right? So 0, 0 will be divided to 0 and 0. 1, 0 is divided into 1 and 0. 1, 1 is divided into 1 and 1. But if we want to divide 1, or if we want to divide individual 0, so that cannot be. So it is called atomic, which has only single value. Here also, whatever instruction that we'll use here, we consider as a atomic. It means that at one go, all the instruction is going to execute, and there is no provision of interrupts. That is called atomic. So all these instructions are called atomic instruction or non-interruptible instruction. So we consider whatever instruction we'll use here is non-interruptible. Now, in the hardware, we have two solutions. One is the test set instruction, another is the swap instruction. So we'll see these two solutions one by one. So the first solution in the hardware synchronization is test and set instruction. Okay. Now let's talk about this test and set instruction. In this, we have, so this particular thing means from here to here is actually, this particular is actually atomic. These instructions are atomic. So in the actual hardware solution, we have the instruction just like which will execute in one cycle. But here you consider as a C code. So we have just converted the instruction, hardware instruction, into the C code. So this is the C code or C++ code, whatever you can see. So this is a high level code. But if it is executing, it will execute all the instruction at one go or at one cycle. So there is no interrupt. Now it says that there is a returning value as Boolean. Test and set is the function name, and it is taking a pointer. Which pointer? Boolean pointer. The pointer name is target. What it is doing? It is taking the value, whatever the value of target is, to a variable RV. RV is also a Boolean variable. And after that, whatever value that target is pointing to, it will make it is true. And then it is going to return the value of RV. Okay. So this is a simple test set instruction. Let's see the logic behind it. So here we have the entry section. So this one is the entry section. And you can see here, after the critical section, this is your exit section. So entry section, it says that test set will call this particular function, this function, with a reference, means with the address of lock. And if it is giving you true, then will be in the loop. If this will giving you false, then we'll execute the critical section. So once we'll execute this particular critical section, after that, we can go to the exit section. It says that lock will become false, and we'll execute whatever the remainder section is. Okay. Now here it says that shared Boolean variable lock. So as I told you, hardware solution will look for a variable called lock. And here the solution, it says that this lock variable is initialized with false. So the initial value of the lock variable is false. Okay. Now let's execute this particular code and try to understand what it is doing. So I think you understood the code, right? So as I told you, this part is atomic. Atomic means at one go it is going to execute. But in this part, we can preempt at any point. So you can say this is atomic and this is non-atomic or preempted. This may be non-preempted. Now the lock value is starting with false. So if it is starting with false, let's say lock is nothing but a variable, right? So I'll consider it is a variable. Now lock is a variable. Because it is a variable, it has been assigned some memory. So let's say there is some memory address I am just writing here. 1020 is the memory address. And what is inside the memory address? The first value is false because it is initialized with false. Now let's go to this loop. It says that while test and set ampersand lock. Ampersand lock means the address of lock we are providing here. So what is the address of lock? 1020. So 1020 will be provided to this particular function, right? We are calling the function with a parameter. So parameter is address, and address we are giving here. So what address we are giving? 1020 to a pointer which is called target. So you can see here, target is nothing but a pointer, right? And what pointer will do? Pointer will hold the address of any variable which is assigned to it. So it will hold the address because the address that we are passing here is 1020. So the value in this target is 1020. So I think you understood this. That we have assigned here. Now we have a variable, another variable called RV. Is a Boolean variable. And in the RV, what we do is we give the asterisk of target. Means whatever the value, what is target actually? Target is nothing but, if I'll print target, so what it will going to print? What is the output? The output will be 1020. If I'll print asterisk of target, then what it is going to print? It is going to print false, right? So the value of the target, because target is a pointer, the value is nothing but the address. But if I'll say asterisk of target means in this particular address, what is the value? So in this particular address, F is the value, right? So it is going to print F. So if I'll say asterisk of target, this will be F. So F will be assigned to, or the false will be assigned to RV. So what is the value of RV? Is false, right? Now after that, asterisk of target will be equal to 2, means whatever the target is pointing to, that particular, in that particular memory's location, will put true, means this false will be overwritten with true value. Got it? And after that, it is going to return RV. What is RV? RV is false. So the false it is going to return, and it is coming here. So when it is coming here, because this function we have called, and that function is returning false. So while false means this while loop is not going to execute, and we are going out of the loop. So once we are going out of the loop, we are going to execute the critical section. Once we'll execute the critical section, after that, in the exit section, what is the code? The code is lock equal to false. Means whatever the lock value is, we are putting false again. Whatever the lock value is, we are putting false again. So I think you understood, right? So this is how it is executed. Now let's talk about our parameter, whether it is fulfilling the criteria of critical section or not. So what are the criteria? Mutual exclusion, progress, and the third one is bounded waiting. So it exists or not. Okay. So first we'll see the mutual exclusion. So let's say we have two process, P0 and P1. Let's say at very first P1 is executing this code. Okay, so if P1 is executing this code, then what will happen? So if P1 is executing the code, and definitely the false value will be, the lock value will be assigned here. Whatever the lock value is just the initial one, right? It is false. So 1020 will be given here. 1020 is coming here. RV value will become false, and after that target will become true. This will become true, and then this RV value will be given here. So it will be given here, and once it will be given here, because it is returning false. What is the value of RV? RV is false, so false will be returning here. Then it will execute the critical section. So right now P0 is in the critical section. Okay. Now at the same time, can we put P1 also in the critical section? Let's see. Now P1 is executing the code. If P1 is executing the code, it will execute the code from the beginning. So what is it in the beginning? While, test, and set lock. So what is the value of lock? Lock is true, and the address is 1020. So when 1020 applied here, it will come here, and RV value will be assigned whatever the value which is pointed by the pointer. So what is the value which is pointed by the pointer? It is true. So this particular RV value will become true, right? Now after that, whatever the target value is, it will become true. So whatever the target value is, it is already true, so we doesn't have to modify it. Then it will return RV. Once it will return RV, it is true. So it is true, it is returning here. So once it is returning true, you can see here, because while loop will become true, it will be in a loop. So P1 will be in a loop if P0 is in the critical section. Getting it? So if one process in the critical section, this code will not allow other process to go to the critical section. So mutual exclusion exists. Getting it? Mutual exclusion exists. Now let's go for another solution, another criteria. What is the other criteria? Other criteria is called progress. Other criteria is called progress. Okay. So what progress says? The progress says that if an interested process want to execute the critical section, it can execute. Nobody will stop it. So let's say the lock value, because it says that it should always initialize with false, so we'll initialize with false. Let's say P0 is executing it first. So we have one process P0. We have the process P0 and it is executing this code. So at very first, it is going to execute it. So lock address will be assigned here in the target. Target value will be 1020. Then whatever the target value is, it will become true. So this will become false from true, and RV will be returned. So whatever the RV value is the target value of the previous one. It will be false, and false will be returned here. Then while is false, so while loop will out of the loop, and then will be in the critical section. Once we are in the critical section, we are going out and will make lock as false again. Lock as false again, right? So P0 has done. Let's say P0 again want to go, because P0 is again interested, it want to go. Can it will go? Yes, it can go, because the value is false here, the same thing has been done. And the P0 will go here. Now P will execute at another time, and this is the status again. So the status is not going to change, it will be the same as this. Okay. Now let's say P1 is interested to go. P1 is interested to go. But P0 is also interested to go, and P0 is going here, and CPU is assigning P1, sorry, P0 to the critical section again and again. But P1 is also interested, but P1 cannot go here. That is possible because we doesn't have any variable which will talk about the interest of the process. So if one process is executing here again and again, it can go. Another process which is waiting here will not get the chance to go into the critical section. So progress doesn't exist here. Now, what about the bounded waiting? Bounded waiting also doesn't exist here. Now, in the same case, if P0 is executing this particular code and getting out, again executing, getting out, again executing, getting out, P1 is interested, but because P0 doesn't have any boundation that P0 how many time it will go to the critical section, so we doesn't have any resource where we can do that. So bounded wait also doesn't exist here. P1 is waiting for a longer period of time, and P0 is getting into the critical section again and again, and we doesn't have the provision to do anything. So here in this particular case, which is a test set instruction, is a hardware solution for that. Here we are never going to get the interest of any process. If any process, if critical section is free, so any of the process can go into the critical section. But here we doesn't have any boundation. So if one process is waiting, so CPU doesn't distinguish between two processes, which process is waiting and which process doesn't waiting. So you can see here, progress doesn't exist as well as bounded wait doesn't exist in this particular solution. So do we have any solution which will satisfy the progress and the bounded wait? The answer is yes. We'll do some modification in the existing solution and we'll try to modify it, and we'll see that the progress exists or not. So we have a solution. See, this will be the same. Okay, this is the same. This is your test set instruction. Okay, this part is the test set instruction. This is your a logic. This logic is giving you mutual exclusion, but is not giving you progress and bounded wait. So with the same instruction, can we have another logic? So this is another logic. The instruction is same. Okay, the test set instruction is same, but the logic is here different. Now here we have some different variables. We have waiting is a variable. We have key as a variable. You can see here we have j as another variable. So we have different type of variable exist here. We have lock, another variable. So we have different type of variable exist. Now, could you tell me which one is a shared resources here? So the shared resources will be the lock. Lock will be the shared resources. Okay. And waiting is also a shared resources, which will be shared by different processes. Now here you can see even two processes cannot be achieve progress and the bandwidth. Here in this particular solution, we can achieve mutual exclusion, we can achieve progress, we can achieve bounded wait, for n number of processes. N number of processes. Getting it? With this particular logic. Let's see how we can do that. Let's try to understand the code first. So what is the code? Code is waiting. Waiting will tell about the interest of any process. Let's say we have n number of processes. Let's say we have the process P0, P1, P2, P3, P4. Let's say we have n equal to 5. It means we have 5 number of processes. Let's say we'll start this logic with P0. Okay. Now if we'll start with logic with P0, waiting of I is nothing but 0, which will tell the identity of it. Okay? So I can consider as Pi at any instant of time. So you can see the waiting is an array of size 5. 1, 2, 3, 4, 5. This is the for 0, the P0, this is for P1, this is for P2, this is for P3, and this is for P4. So for initially all are false. Okay, initially all these values are false. Okay. Okay, so waiting of I equal to true means what we are doing is, it says that waiting of all the value are false. It means that all the value want to go to the critical section. Let's start with the P0. If we start with the P0, then the waiting of 0, we have to make it true. This value, we have to make it true. And then key equal to true. So every process has a local variable called key, and this is also true. Now, after that, we have a loop. It says that while waiting of I and key, if this is true, then we have to change the value of key to test set ampersand lock. Okay, and you know that lock is a variable which has the address, let's say 1020, and it has the value false at the very beginning, right? That we have already seen. So waiting of I and key. So what is waiting of I? Waiting of I means waiting of I is waiting of 0th position is true. So it is true. And key, what is the value of key? Is true. So it is also true. If both are true, then the value is true. Then it will be inside the loop. And this is the inside the loop, right? And it says that key is equal to test and set ampersand lock. So we are calling the function test and set with the address ampersand lock. So what is ampersand lock? Is 1020 will be assigned to the target. What is a target? Target is nothing but a pointer which is pointing to the address 1020. This targeted value will be assigned to RV. So what is RV? RV will become false because the value here is false. After that, the value of that target will become true. So this value will become true. And then we'll return the RV value. So RV value is false. So false will be written here to the key. Done. After that, because once the condition is satisfied, we have to look for the condition again. So once we go to the condition again, it says that weighting of I. So what is weighting of I? Weighting of I is true. It is true. But what is the key? Key value is false here. So it is false here. So if true and false, so definitely it will be false. If it is false, it will go out and execute this. What is this? It says that weighting of I equal to false. Now what we'll do is we'll make it the weighting of I as false. And then it will go to the critical section. Getting it? Now it will execute the critical section. It will come out from the critical section and look for the logic again. This is the exit section. Means every process has to execute these instructions once it will execute the critical section. Okay. So this is how it happened. Now let's go and find it out whether the mutual exclusion exists or not. Okay. So let's see mutual exclusion exists or not. So at that particular time, let's say P0 is in the critical section. So can we put P1 into the critical section? So here it was, what was the value? It was false, right? It was false. Here we have given the false value. Weighting of I is also become false and it is in the critical section. Let's say P0 is in the critical section and P1 want to execute its critical section. So can we, should we have to allow? We doesn't have to allow, right? So what we do? Let's say P1, weighting of 1 will be true. So the weighting of 1, this will become true first. So this value will become true first. After that, the key value will be true. So as I told you, every process has its own local key variable. So this will become true. Now after that, while weighting of I and key, so what is weighting of I? Weighting of I is true and key is also true. So both are true. So both are true, then it will execute this. What is it? It will call a function with the lock. So what is the value of lock here? Value of lock here is true. True will be assigned here. Now RV value will become true because the true value will be given to RV and target value will be true. So it is already true, it doesn't have to do anything. And then it will return the RV value. So RV value will become true. So key is true. It is not false, it is true only. Then again it will be in a loop. True and true will be true again. So you can see here, P1 will never get a chance to go out from the loop and will be here for all the time. So P1 will not getting the critical section. Are you all getting it? So here P1 is interested, even though P1 will not get a chance to execute in the critical section. Why? Because P0 is already in the critical section. So what we can say? We can say that mutual exclusion exists. If one process is in the critical section, no other process is allowed to go into the critical section. Okay. Let's see the progress. Whether it provide the progress or not. So what is the meaning of progress? The progress is one process interested to go into the critical section, it can go or not. So let's start with the beginning and assume that P0 has started it. Which one? P0. Lock value was false. P0 is starting it. P0 is starting it. So 0th value will be true. Here it will be true. And it will make key also as true. key also is true, and it will be satisfying the loop. Then it will call the test and set lock. So what is test and set lock is 1020 will be assigned to the target, and f value will be assigned to the RV. So what is the value of RV? RV will be false. This value will be false, right? Now the target value will be the asterisk of target value will be true. So what is asterisk of target is nothing but 1020 location. It will be true, and the RV will be returned. So key value will be false. Once the key value will be false, it will go out of that, and it will say waiting of I will be false, and it will be in the critical section, and it will execute the rest of the thing. What is the rest of the thing? The rest of the thing is to find out the interest of the other process. So what is the logic here is, here it is a variable called j. So we have to find out the variable j equal to I plus 1 mod n. So what is I? I here is 0. We are executing the 0, p0. So it will be 0. 0 plus 1 is 1. 1 modulo, and what is the value of n? Is 5. So 1 modulo 5 is 1. So the j value will be 1. While j is not equal to I. So what is the value of j? J is 1. 1 is not equal to 0. Yes, it is true. And weighting of j. What is weighting of j? Weighting of j. J means 1. Weighting of j is false. It is false, right? So it is false. So false, not false is become true. So both will become true. So true and true will become true. Then it will execute j equal to j plus 1 mod n. What is j? J is 1. 1 plus 1 is 2. 2 mod n will become true. And again it will go and see it. So what it is doing is, it is incrementing the value of I up to n, and it will see whether anybody is interested or not to go to the critical section. Let's talk about this. Let's say P0 is in the loop here, and P1 suddenly being interested to go to the critical section. So what it will do first, it will make it waiting as true. It means it is showing its interest to execute into the critical section. And there is a local variable called key is also true, and then this will become true, and it will call the test set lock. Once it will call the test set lock, weighting of I was false, so this will be false after that. Now this value will be go here, RV will be false here, and then it will be in a waiting again. Now this will be false, and P1 will go to the critical section. Now what is happening here is, while P0 is testing whether other process exist who want to go to the critical section, other process means P1 is executing into the critical section. So you see, whatever process is interested can go to the critical section, and P0 has to wait to again go to the critical section. It need to see all the processes whether they are interested or not. Here progress exists, because if P0 has done its execution, P1 is going to execute into the critical section. Once P1 will be out of the critical section, another process can go it, but P1 has to check for other interest. That has to be done. Means if other process is just interested, but it doesn't executing the critical section, so other process has to respect their waiting, and bounded wait also exists. Let's see how the bounded waiting is existing here. So let's assume that P0 has done its execution and it is in the while loop. So the J value here for P0 here for P0 will be 1 and P0 is in the loop. At that particular time, P1 is interested. P1 want to go. If P1 want to go, then you can see this value will be true. Once this value will be true, P1 has the key value also. It will also become true. And at the same time, if P0 is checking the weighting of J, which is 1, which is true, and it says that true not, it will become false. So it will go out of the loop here and it will check J is equal to I or not. So J is 1, I is 0. So this doesn't exist, then it will go to the else part and it will make J of I as false, and after that J can go to the critical section again. So you can see that means J means 1. 1 can go again into this particular critical section. So you can see that if P0 is executing its critical section, then P0 will check rest of its process whether anyone is interested for the critical section or not. If nobody is interested, then only P0 will get the chance to again go to the critical section. If any of these exist with the interest, then they will be allowed into the critical section. So here you can see that if somebody is waiting to go to the critical section, this particular logic is allow it to go to the critical section. The same thing happened to other processes also. If let's say P0 is executed and at the same time P1 has shown its interest, but because P0 is already in the critical section, P1 cannot go. But once P1 is out from the critical section, it will look for other processes whether anyone is interested or not. If anyone is interested, it will make sure that this process will go to that particular critical section. Then let's say P1 will go to the critical section. Once P1 will go, let's assume that P2 is interested on that. So before again P1 will be going into the critical section, it will find it out whole process P2, P3, P4, P5, P0, who is interested? Sorry, P0, who is interested to go to the critical section? If nobody is interested, then only P1 will get the chance to go to the critical section. So in this solution, mutual exclusion exists, progress exists, as well as bounded wait is also exist in this particular solution.